All right, here we have our notes on section 2.4, complex numbers. So the reason complex numbers were created is a long time ago they were trying to solve this equation, x squared plus 1 equals 0. They were not able to because they would use their traditional subtract 1 to both sides, and they ended up having to take the square root of 1. They couldn't get an answer to this. So because they couldn't define an answer, they decided, all right, we might not know what it is. We're going to define our own answer. We're going to call the square root of negative 1 I. So that same idea, meaning where it originally came from, I squared was equal to negative 1. You square both sides. That's really why you may have heard in the past I squared equals negative 1. But we'll get to that more in future slides. What you're going to see is I, it's still very similar. It's very similar to a variable. It's an unknown, yes, but it's an undefined number, but it can still be treated similar to all variables. We're going to add it, subtract it, multiply it, divide it, and the last part here, when you use I, you are using complex numbers, and complex numbers has a standard form, a plus bi. So a is usually the whole number, the real number portion, and then bi is kind of the imaginary portion. So you can have a real number plus an imaginary number. That's a complex number in general. So it's a little bit of notation. Essentially, when you use imaginary numbers, you can use, like I said, a real number plus an imaginary. Okay. All right. So, like I said before, we're going to be able. You can add and subtract just like you would like terms. So, just like you would combine 3x with x, here you're going to be doing the same type of combining like terms. And what I mean by that is we do a little bit of distributive property. 3, that's going to be plus 2 minus 3i plus 5 plus I. So we look for our like terms, 3, 2, and 5 all combine to 10. Here you're going to have minus 2i, those combine right there. It's straightforward. So actually, because I know you've combined like terms in the past, why don't you try this one and we will go over it tomorrow in class. But give this one a shot now and we will go over it tomorrow. Alright, going back to the first slide, this is what I was talking about. We all know the definition for I. The definition for I is the square root of negative 1. So if we were to square both sides there, then I times I would be I squared, which is the same as the square root of negative 1 times the square root of negative 1, which is the square root of negative 1 squared. So we would call that just I squared. We could now define as just negative 1.
Officer Connolly to the office, please. Officer Connolly to the office, please.
Right. Keeping going, we want to try to figure out I to the third, and the tricky part here is I times, if we think of it this way, we already know this is I squared times I. Well, we already figured out I squared. I squared is negative 1. So we have negative 1 times I, better known as negative I. So when we're looking at I to the third, we're going to be able to simplify it down to I, the opposite of I. And when we're looking at I to the fourth, I'm going to write it out using our longhand notation. That's I times I times I times I. Well, going back to what we talked about right up here, we have I squared, which is equal to negative 1, and we have I squared, which is also equal to negative 1. If you multiply negative 1 times negative 1, it is telling us I to the fourth is positive 1. So there is a little pattern here. All right, you're always going to call I. I to the first is always going to be I to the first. But any higher exponent of I can always be reduced down. And if it's I to the fourth, it can reduce down to 1, which is a nice, easy, friendly, real number. Okay, so let's keep going. There's a pattern here with I to the fifth. So I'm going to write I to the fifth as I to the fourth. I'm going to write that as I to the fourth times I. That is I to the 5th is the same as I to the 4th times I to the 1st. Well, going back to what we talked about just right above, I to the 4th, we know that is equal to 1. So 1 times I to the 5th simplifies down to I. Now there is a pattern here. We'll go to I to the 6th and we should be able to see it. If you break down I to the 6th to I to the 4th times I to the 2nd, well, we already know I to the 4th is equal to 1. We know I to the 2nd is equal to negative 1. So total, we know I to the 6th is equal to negative 1. If you had to take a guess, try to figure out what I to the 7th, I to the 8th, and come to class tomorrow ready to explain what the pattern is involving I raised to a power. All right. Here we'll be multiplying multiplying using imaginary numbers, or multiplying using complex numbers in I. And what I'd like to focus on here is, you know FOIL, you know the distributive property, you know your properties of exponents and radicals, they all still apply. Now you're just doing it with I. So square root of negative 4, we know that simplifies down to 2I, because, well, if you want to break it down a little more, you could say that's the square root of 4 times the square root of negative 1. Square root of 4 is 2. The square root of negative 1 we're calling I. You could do the same thing with radical 16. You would simplify that down to the square root of 16 times the square root of negative 1. And you would say now times, that's 4 times I. So we are multiplying 2I times 4I. Well, 2 times 4 is 8. I times I is I squared. We would never leave this as an answer, because you're never going to leave I with an exponent in an answer. We know that I squared is equal to negative 1 from the previous slide. Final answer, negative 8. What I talked about earlier in our second problem, it's essentially a FOIL problem. The only difference with FOIL is you're still going to do the same first, outside, inside, last that you're used to. So I hope you see where I'm getting 8 plus 6I minus 4I minus 3I squared. So combine the like terms you normally would in the center. 8 plus 2I minus 3I squared. And last but not least, going back just like the last problem, we cannot leave an exponent in an answer. So we have 8 plus 2I. This is really minus 3 times negative 1. I'm going to call that all plus 3. And you will most of the time have a couple more like terms to combine. 11 plus 2I, final answer. And in the bottom here, we have a little distributive property. 4I times the quantity negative 1 plus 5I. So you do, what's going on here? Try this again. All right, so we do a little bit of distributive. You're going to get negative 4I plus 20I times I is I squared. Same reasoning as before. Never leave your exponents in your imaginary numbers. So you're going to call that negative 4I, and that's going to be, you could say plus 20 times negative 1. A lot of people will just simplify that and say plus negative 20. And the most common way you're going to see this is in complex form. You usually put the whole number first and then the imaginary portion after. So negative 20 minus 4I. All right, so one of the most important vocabulary terms of this section is conjugate. And if you're given an imaginary number, or in fact any two terms, all right, something plus something, well, the conjugate is something minus something. So the conjugate with imaginary numbers, if you have the conjugate of a plus bi, a regular old complex number, its conjugate is a minus bi. You switch the plus to a minus, and you've got the conjugate. Now, there's a reason multiplying by the conjugate is so important, and it comes up so often. I hope you can guess the conjugate of 3 minus 5i. That's 3 plus 5i. All I did was change the plus to a minus. And what's really happened here is that this is a difference of squares. So when I say difference of two squares, when you talk about your difference of two squares, you would usually factor a squared minus b squared. 2, you would factor this 2. A plus b, a minus b. Something plus something, something minus something. That's exactly what we have here. So what we are actually doing is taking this portion here and foiling back to this. The foil of a conjugate is actually very straightforward and very simple. 3 times 3 is 9. All right, now, I usually never write this step of 3 times 5i because it's plus 15i. The reason I never write it is because the middle, negative 5i times 3 is negative 15i. If you notice, these two will always cross out, so a lot of times I skip it, and I just do negative 5i times negative 5i, which is negative 25i squared. And to sum up again, we never leave a exponent with I in our answer, so we would say that's 9 plus, that would be positive 25 now, so final answer here, 36, final answer. So by multiplying by a conjugate, we took an imaginary and actually made it a whole number. That'll happen anytime you multiply by a conjugate. All right, so the reason we use that multiply by a conjugate is because it'll rationalize a denominator. So if you do have a complex number in the denominator, you can rationalize it by multiplying by the conjugate. So here we have a fraction. Again, we cannot leave I in the denominator because I stands for square root of negative 1. You guys already know you can't leave square roots in denominators. You need to rationalize it. So this is the same type of rationalization process. We focus on the bottom and say I need to multiply by its conjugate. That's 4 plus 2i. Alright, so it's a big FOIL problem on top. On the top, when I FOIL, 8 plus 4i plus 12i plus 6i squared. On the bottom, I'm going to go the straightforward, more simple version. I'm going to just do 16. 4 times 4. I'm also going to get the negative 4i squared.
Good afternoon. Brian Sear, please call extension 149. Brian Sear, please call extension 149.
So I simplify the top. I get 8 plus 16i. And I'm going to write that, instead of writing plus 6i squared, I'm going to write minus 6 because I'm going to get rid of that I squared that we know is equal to negative 1. Right here.
Mrs. Cohen, please call the office. Mrs. Cohen, please call the office. Thank you.
On the bottom, copying over the 16. Of course, this time it's no longer going to be minus 4i squared. It's going to be plus 4. So when I simplify this down, I'm going to combine a couple like terms. 8 minus 6 is 2 plus 16i, all divided by 20. You could do one more small simplification. What I mean is there's something in common on the top. You could factor out a 2. Leaves you with 1 plus 8i, all divided by 20. And 2 over 20 is going to reduce to 1 over 10, meaning our final answer, 1 plus 8i, all divided by 10. Did that not record? Oh, there it is.